Welcome everyone to this short lecture. I am Onindo Bhattacharjee and today I will be talking about the active mode operation of a bipolar junction transistor. So let us first talk about what is a bipolar junction transistor. So compared to a typical diode, a bipolar junction transistor is actually a three-terminal device where it has a distinct emitter region, a base region, and a collector region. So the key idea here is that the base region will have a different doping compared to the emitter and collector region. Here we have shown an NPN type doping, so we call it an NPN transistor. We can also have a PNP type doping, and we would call that a PNP transistor. So let us focus our further discussions, assuming that this is an NPN type transistor. Now, why do we call it a bipolar device? It's a bipolar device because the current flow is contributed by both the electrons and the holes, which are oppositely charged, hence the name bipolar. So the target or the benefit of this bipolar junction transistor device is that we can control the current through one terminal using the voltage of the other two terminals. If you recall that in a typical diode, the current of the diode is actually controlled by the voltage applied across the two terminals. But here we have a additional control over the current across the terminal by using voltage across the other two terminals. And to achieve this target, we have made several, or the people that have developed the bipolar junction transistor have made several design choices. The design choices are represented actually in this table. So what can we control while designing this device? We can actually control the doping level, how much dopant that we introduce in these specific regions, and what would be the width or the geometry of these specific regions. So in a typical bipolar junction transistor, the emitter region is very highly doped with a moderate width. The base region is lightly doped and is very, very thin. And the collector region is actually moderately doped, but it has the highest width compared to the emitter or the base region. Although in this diagram, the width is not properly represented. So if you look at this diagram, we can see that there are two junctions. There's an emitter base junction and a collector base junction. And if we recall from our knowledge of diodes, we know that a junction can be biased in two ways. It can either be forward biased, where the P region has a higher potential, or it can be reverse biased, where the N region has a higher potential. Since this device has two distinct junctions, we can bias it in various ways. And depending on these biasing configurations, we have different modes of operation. We have a cutoff mode where both the junctions are reverse biased and no current flows. We have a mode called active mode where only the emitter based junction is forward biased and the collector based junction is reverse biased. And we have a saturation mode where both the junctions are forward biased. In this short lecture, we will be specifically focusing on the active mode of operation because it is typically used in amplification applications, which we will study further. So what happens in the active mode of operation? So recall that we have said in active mode operation, the base emitter junction is forward biased, and it is actually so, as we can see in this diagram. The VBE applies a higher potential in the P region compared to the N region, thus it's forward biased. And the collector base junction is reverse biased because the higher potential is applied to the N region using this VCV source. So in our typical knowledge of diodes, we see that when a junction is reverse biased, no current flows through that junction except a very minor leakage, which we can ignore here. But in forward bias, if the applied voltage is higher than the threshold voltage, we expect a current to flow. And let us assume that this VB is higher than the threshold voltage of this PN junction. So a current is flowing through this junction. Now this current have two components: the holes injected from the P region to the N region, then there are the electrons that are being injected from the N emitter region to the base region. So what happens in this junction when it is reverse biased? So in our typical diode, we know that when no bias is applied, due to the concentration gradient of electrons and holes in the two doping regions, we see a depletion region to form, which has an internal electric field being applied here. And when we apply a reverse bias into that junction, what happens is that the depletion region gets larger and wider, and the amplitude or the magnitude of the electric field goes way higher. The biasing voltage actually adds to this already existing electric field. So what happens in this junction is that there is a very wide depletion region with a very high electric field acting just inside of it. So when the base emitter junction is forward biased, electrons are being injected from the emitter region to the base region. If such electrons get into this depletion region of the collector base junction, due to this electric field being present, the electrons will be drifted into the collector region to this source, right? If we look at the electric field direction, and since electron has a negative charge, its direction would be from the base to the collector region, right? So now how to make it possible, right? Like, we want that the electrons to go through this collector junction. How do we make that possible? To make this possible, what we can do that is we can make the base region very, very thin. So if we make the base region very thin, the electrons coming here will readily get into this depletion region. And another thing that we can do is that we can very lightly dope this base region so that the recombination with the holes is very, very low, so that the electrons again can drift through this depletion region. So we have validated our design choices. So why do we want that electrons to drift to the collector region? Because if that happens, you see that in reverse bias there is no current. Typically there is no current flowing through the junction, but here we are getting a current that is being caused by this forward bias current of this junction, right? This is really important. If you focus on this point here, this is the entire point of a bipolar junction transistor, is that the forward bias current of this junction is contributing to the collector current. Or in another words, if I say that the current in the collector terminal is being controlled by the forward bias voltage of the base emitter junction. So what our target was to control the current through this terminal uh, by the voltage through the emitter and base terminal. That was our target, that to control the current of one terminal through the voltage of other two terminals, that we have achieved in this active mode of operation, right? And if we mathematically express this, we already know this equation from our typical PN junction equation, but we express the collector current as a proportional constant of the base emitter biasing. And if we focus on the base current should also be proportional to this base emitter biasing. But the base current should be relatively smaller compared to this collector current due to our design choices. The base design choices are what? The base is thin and it has a very low doping. So the most of the electrons injected from the emitter should get swept into the collector region, and the base current should be very, very small. So we can represent the base current as a fraction of the collector current. Here beta is a constant which is higher than 1, obviously, because base current is smaller than the collector current. And we call beta the common emitter current gain, and this common emitter current gain depends highly on the width of the base and the doping level ratio of the emitter and the base. And we can also physically validate that it's intuitive that if the width of the base is very high, then less electrons will be swept into the collector region, so the collector current will be smaller and base current would be higher, so beta would be what? Beta should be lower. Similarly, if we increase the doping level of the base, beta would also be lower, right? So beta is typically an important parameter while we are designing the circuits of amplifier circuits, right? So we have expressed beta here. And note that the collector current actually comes from the emitter current, right? The injected electrons in the emitter base junction contributes to the collector current. So we can also express the collector current as proportionally to the emitter current, which we have expressed using this constant alpha, which is called the common base current gain. And we can represent the emitter current using this collector current configuration as here. Now, if we apply Kirchhoff's current law in this base node, if we apply Kirchhoff's current law, we will see that the base current and collector current sums up to the emitter current, right? Emitter current gets divided into the base and collector region. So we can write that the emitter current is actually the sum of the base and the collector current. And in this equation, if we plug our previous proportional relationships, that the collector current is actually proportional to emitter current through this constant alpha and proportional to the base current through this constant beta, we can get or derive a simple relationship among the alpha and beta, which is this: 1 by alpha minus 1 by beta is equals to 1. In a typical bipolar junction transistor, alpha is actually very close to 1, but it's always smaller than 1. So typically 0.999 or 99 is a typical value, and the beta value is typically 100 to 300 based on our design choices. Now, if we look at the circuit models, here we see a bipolar junction transistor. Both of them are bipolar junction transistors. There are 3 terminals: emitter, base, and collector. How do we identify the emitter terminal? The emitter terminal should typically have an arrow associated with it. If the arrow is coming out of the base terminal, it's an NPN BJT model, and if it is going into the base terminal, it's a PNP BJT model. And here we are showing the circuit of the active mode of circuit for the active mode of operation, and here we are showing a large signal equivalent circuit model. What this actually means is that this bipolar junction transistor is modeled using a diode and current control current source to simplify our calculations in a typical circuit application. So here a diode is forward biased in the base emitter junction, and a current control current source is actually represents the collector current, which is actually proportional to the base current, as we have derived in our previous mathematical equations. So it correctly represents the model that we have previously discussed. So here's a summary of my lecture. So what we have done is we have shown BJT, which is a 3-terminal device with 3 distinct regions: an emitter, base, and a collector. In forward active mode, the emitter base junction is forward biased and the collector base junction is typically reverse biased. And in the description of the active mode of operation, we have seen how the collector base junction current is actually controlled by the bias voltage in the base emitter junction. And finally, we have said that the forward active mode operation is typically used in amplifier. So all the figures presented in this short lecture are actually taken from the microelectronic circuits by Cedra and Smith, 7th edition. And this is the end of my short lecture. If you have any further queries, you can contact me at my email given here. Thank you, everyone.